Hi there, my name is Clark Tantitam Thawan. I'm from Monash University, Australia. I'm here to present the paper titled SQAPlanner, Generating Data-Informed Software Quality Improvement Plans. This paper is accepted at IEEE Transactions on Software Engineering, or TSE. This work is in collaboration with Delini Rajpaksha, Jirayut Jianpakdi, Christophe Bergmier, John Grundy, and Ray Bantai, all from Monash University. As everyone knows that software defects are very costly and prevalent, but they are very hard to predict and prevent. Thus, practitioners want to find and fix defects as early as possible instead of fixing them in productions. So SQA practices like exploratory testing or code review are adopted in many organizations, but such activities are still very time-consuming and expensive. So let's imagine that you work at Google with millions of lines of code. You just have no idea which files are likely to be defective in the future, or which files should be reviewed first. Such ad hoc decision making could lead to suboptimal SQA resource prioritization. Developers cannot efficiently and effectively find the highest numbers of defects given the limited time and resources. To address this challenge, defect prediction models have been proposed to predict if a file will be defective in the future or not. Traditionally, we use historical data from previous releases as a training data to build a defect model, and then we apply the defect model to each file in the current release or testing data to generate the predictions. And such predictions will help developers prioritize the limited resources on the most risky files, and the most important factors from the model level also help managers develop better quality improvement plans as well. And such defect prediction models have been used in many software companies like Google and Microsoft. Let's consider Microsoft Code Defect AI as an example. So this defect prediction tool aims to predict if this Java file is likely to be defective in the future or not. And this tool predicts this file as yes with a confidence score of 70. And this tool also uses LAM, which is a model-agnostic technique, to generate an explanation. And like in this case, lines of code class method LOC contribute the most to the prediction. And it implies that developers should do something about LOC to mitigate the risk of having defects. Why this tool is quite explainable, but they are still not actionable yet? Importantly, practitioners still don't know what should they do to decrease the risk of having defects, and what are the risk thresholds for each metric, right? Like in this case, LOC contribute the most to the prediction, but the question is that how small a file should be to be considered as non-risky. To address this challenge, we perform a series of investigations with the goal to help practitioners make better data-informed SQA planning we try to make the defect prediction models more actionable. So first, in the IQ1 and the IQ2, we conduct a qualitative survey with practitioners to better understand the practitioners' perceptions of the SQA planning activities. And then we propose an SQAPlanner approach and perform an evaluation in the IQ3 and IQ4 and IQ5. And finally, we develop a visualization for our explanation and conduct a qualitative survey with practitioners to investigate if our explanations are better than the state-of-the-art Microsoft Code Defect AI or not. For the first two research questions, the qualitative survey, we received a total of 50 responses from practitioners. We found that over 50% of the respondents perceive that SQA planning activities are important, being used in practice, but still time-consuming and very difficult. We also found that for the SQA planning activities, they are still manual. For example, they often use the documentation or the manual review checklist to ensure that they are not repeated in the future. So we can conclude that a data-informed SQA planning tool is needed to support QA teams make the better decision and policy makings. So we propose SQAPlanner, which is a local rule-based model-agnostic technique to generate explanations and actionable guidance. Conceptually high level, our approach consists of 3 steps. First, we use crossover and mutation to randomly generate synthetic instances around the neighborhood of an instance to be explained. Then we construct an association rule model using magnum opus in order to generate an association rule explanation that achieves the highest accuracy. Let's assume that we have a defect model with predictions to be buggy or clean. Our SQAPlanner will take model and an instance to be explained as an input in order to generate different types of association rules. Like in this example, this rule means that this file is predicted as defective since LOC is greater than 100 and the ownership degree is less than 0.8 or 80%. So this kind of knowledge will help developers understand the most important aspects that are associated with the software defects. For this case, it's going to be LOC and the ownership, and also help developers understand the risk threshold. That means when LOC is less than 100, the model may reverse the prediction from defective to clean. So, to evaluate our approach, we investigate how accurate are our rule-based explanations. We measure the quality of the rules with respect to the association rule measures like coverage, confidence, and lift. We find that our approach outperforms the state-of-the-art approach like law and anchor for both 3 evaluation measures. We also investigate how stable are the rule-based explanations. So we measure the similarity of the explanations when they are regenerated using a Jaccard coefficients. And we found that our approach also outperforms the state-of-the-art approaches like law and anchor as well. So we can conclude that our SQAPlanner generates explanations that achieve the highest coverage, confidence, lift, and consistency when compared to law and anchor. Since rules are very complex and are hard to comprehend, we translate the rule explanations into a nice visualization to see if they are, and we're gonna ask practitioners to see if they are more actionable or not. Like in this case, instead of explaining just like why a file is predicted as defective, we actually provide actionable guidance to do, like for example, like in this case, what to do to decrease the risk of having defects. Like the first one, we can suggest that decreasing the numbers of class and method declaration lines to less than 20 lines instead of the actual 34 lines. So again, we ran a survey with practitioners and found that 80% of the respondents agree that this visualization is much better for providing actionable guidance when compared to the Microsoft Code Defect AI. So in conclusion, actionability is very much needed in software engineering, and SQAPlanner is one of the important advancements towards actionable software analytics. So if you are interested in the area of Explainable AI for software engineering, please feel free to check out our online book XAI for SE.github.io. And if you are interested in collaborating with us, please feel free to contact me. Thank you for your attention.